everyone! Today we're going to do part 2 of the lesson that we started in the last class, which we were talking about concentration and rate laws. So I started the last lesson with this exact same slide, and we were looking at how the rate of a reaction can be studied by seeing how the changes in concentration affect the reaction rate. So this is typically done through an experiment and multiple experiments. Down below, we have a table that illustrates ammonium being reacted with nitrite to form nitrogen gas and water. These experiments changed the concentration of both the reactants, and we got data collecting telling us how did the speed or the rate of the reaction changed. From there, yesterday we learned how to take that information and develop what's called a rate law. And the rate law we determined for this example was the rate equals K times the concentration of ammonium times the concentration of nitrite. And both of these were determined to be first order or to the first exponent. The reason we determined that was because we saw that when ammonium doubled, the initial rate doubled. So ammonium doubled, my rate doubled, so 2 to what power gave me 2. And that's the first. We also saw the same thing with nitrite. When it doubled, the reaction rate doubled, so it was also a first order. What we didn't really talk about was this value of K. So once we know the rate law for a reaction and we have a set of reactant concentrations we're able to work with for that rate, we can actually plug those in and calculate the value for K. So for example, if we use the example we were looking at just a few seconds ago, we can use the values from the table to determine the value of K. The way we do that is we go to this table and we pick the first one is usually the easiest, and we see, okay, the rate is 5.4 times 10 to the negative 7th. So in this equation right here, we're going to plug that in for rate. So here you're going to see me plug in 5.4 times 10 to the negative 7. This is going to equal our K value, and that's what we're solving for. And then we have our two concentrations. So where these two concentrations come from is that same table. Make sure you pull it. So if you chose the first rate, you also should choose the first set of concentrations to plug in. Here, you're going to see that I'm plugging in ammonium as 0.01 and nitrite as 0.2. So these are both to first order reactions, so they're just to the first exponent. Here, it's simple algebra, and you can solve for K, which means I'm going to have to take these two values and multiply them together, and then divide them to the other side to get K by itself. And you're going to see that the K value here is 2.7 times 10 to the negative 4th. Our unit here is molarity to the negative 1st and second to the negative 1st, and we're going to talk about what units to use when here in a few slides. Before we get to the units, we're going to actually talk about the magnitude of rate constants, though. Oftentimes, chemists want to compare the rates of reactions and how fast, how slow things happen. So what they do is they typically look at the rate constant to determine this. A large value for K typically is going to indicate that the reaction happens pretty quickly or fast, whereas a small value of K typically means that it's going to be a slower reaction. Now, one thing I do want to write down, and we are going to talk about this, is this rate constant that we've been learning about K. So I'm going to put K in parentheses up here. This rate constant is temperature dependent, which means it's going to be affected whether the temperature was 300 Kelvin versus 150 Kelvin. That matters. So temperature is going to be a big factor. So what units do we use for rate constants? Well, you're going to note that the unit that I used was a little bit different. And the units for a rate constant actually depends on the overall reaction order of your rate law. So, for example, the overall reaction order, hopefully you remember, is M plus N. So what value do I have here? Plus here. The example that I gave was a second order overall because I had 1 plus 1 gave me 2. The units are going to change depending because the units are actually derived from my units for rate versus my reaction order concentrations and to what order they are. So for a zero order overall, your unit is molarity times second to the negative first, or this can actually be written as molarity. And when you see a -1, that means per second. Here, first order overall is second to the negative first, or you can rewrite it as 1 to the second. Second order overall is m to the -1, s to the -1, and third order is m to the -2, s to the -1. Again, you can rewrite all of these as well. Here is one of the two examples that we walked through yesterday. We first determined what our rate law equation was going to be, and then we determined what order overall that it was. So we're going to actually work on part C and D and how to find those. Yesterday, we found that the rate equals K, add that in there, is the concentration of A to the second power. So what we're going to do is now that we have this rate equation, we can actually just plug things in for it. So again, the first thing is just use the first equation. So my rate was 4.0 times 10 to the -5th. And again, you could have used any of these. This is going to equal your K value. And then here, if I use the first rate, that means I have to use that concentration. So here my A concentration is 0.1, and my rate law is telling me to make sure I take that to the second power. So here, if I solve this, I'm going to take 0.1, and I need to take that to the second power, which gets me 0.01 times my K equals 4.0 times 10 to the -5th. In order to get K by itself, I'm going to divide by 0.01, and I'm going to find that my K equals, once I get that into the calculator, my K actually equals 0.004. Here, we need to make sure this is a second order overall. So if we look on our last slide, second order overall gets the unit molarity, -1, S -1. Here, if we were going to sig figs, technically this would have 2 sig figs. So I'm going to add a 0 behind here just to show me I have 2 sig figs. Part D then tells me to calculate the rate of the reaction whenever the concentration of A is 0.050 molarity and B is 0.1 molarity. Now that I know my K, I can actually use that to calculate rate for any concentration. So here I need my rate, so I'm going to write rate, so rate is X essentially, equals my value for K. So I'm using this equation up here in case anyone was confused. My K I found to be 0.0040 times my concentration of A. So my A was 0.050, and we're going to square that number. So here it also gives me a value for B, but since B is not part of my rate, I can actually exclude that because it's not going to affect my rate at all. So here I can plug this into the calculator. I can take 0.050 and I can actually square that. And then I can multiply that by my K value. And when you get that, your rate actually equals 1 times 10 to the -5th. But in order to keep 2 sig figs, I'm going to put 1.0 times 10 to the -5th. And again, rate is always going to be the same units, molarity per second. So there we go. Working through the second example, we have the same thing. Using the following equation, we found this yesterday, that rate equals, add my K in. Can't believe I keep forgetting that. And then we have nitrogen monoxide to the second power, and then hydrogen gas to the first power. And we need to determine the rate constant. So we have a rate. We're going to use the first one. It's the easiest one to use. 1.23 times 10 to the negative third equals K. Okay, so here's NO2. So since I used that one, I need to use this value here. So 0.1 to the second power. And then hydrogen would also be 0.1. So here what I'm going to do is consolidate some things. So let's rewrite this part of the equation. So I'm going to take 0.1 and I'm going to square it. And I'm going to multiply that by 0.1 because of my B value. And I get K equals 0.001. Again, to get K by itself, let's go ahead and divide. And then so when you divide 1.23 times 10 to the negative third divided by 0.001, you get the K value of 1.23. Again, to determine my units, it depends on the overall reaction order. So I have an exponent of 2 plus my exponent of 1 gives me third overall. So if we look back at the slide, third overall is meters to the negative second, or negative 2, and then second to the negative first. So let's go ahead and plug that in. Here, when I actually look at this and I'm rounding to correct number of sig figs, I have 0.1 here, and here I have 3. So here I'm going to make sure I only have 2 sig figs. So 1.2 would be my sig figs. Now, here's the thing. If I have 2 sig figs here, when I actually go to do part D, we don't want to use that rounded number. So we want to make sure to use our unrounded number here. So if I have rate, we want to use our unrounded number of 1.23. And then what we're going to do is we got to plug in our NO value, which they give us as 0.050. Remember, according to our law, that's to the second power. And then we're going to multiply it by our hydrogen gas, which is 0.150. And we can go ahead and plug this in. So I'm going to solve for my exponent first. So 0.05, square that value. We're going to times it by the 1.23. And again, we're going to times that by the 0.15. And we're going to find that the rate, whenever the value is that low, is actually equal to 4.6125 times 10 to the negative fourth. Due to sig figs, I'm just going to round this to 4.6 times 10 to the negative fourth. And since this is rate, we're going to do molarity per second. Okay. And that's the end of today's lesson. If you have any questions, please make sure you ask. And I hope you guys have a great day.